What if I told you that the geometry of a perfect circle, the exponential growth of your bank account, and like the swirling spirals of a pine cone are all secretly the exact same number?
Just wearing different masks, basically.
Yeah, exactly. Welcome to the deep dive. If you're tuning in, you probably already have a few mathematical constants floating around in your head from those old high school
Well,
flashcards.
sure.
You know the ones. You've got pi, which we are always told is strictly for the geometry of circles, right?
Right.
And then you've got E, Euler's number, which pops up whenever things grow continuously, like compound interest.
Yeah, or population growth.
Exactly. And you've probably heard of phi, the golden ratio, that famous number behind proportional beauty and art and nature and stuff like that.
And traditionally, the way we're taught about these numbers treats them like totally isolated VIPs of the math universe. They each kind of live in their own gated community.
Right, totally segregated.
Exactly. Pi is the mayor of Geometry Town. Re runs Calculus City. And Phi is often the art district. The assumption is that, well, never the twain shall meet.
You just pull them out of a toolbox when you have a very specific problem to solve, and then you put them back.
Right. They don't interact. But today, we are tearing down those gated communities.
We really are. We're looking at a source today that totally shatters that fractured view of math. It's this wild, fascinating paper by Chen Kai-chen.
Titled Recursive Geometry and the Emergent Approximations of Mathematical Constants.
Yeah. And Chen is making a massive argument here. He's proposing that these famous constants aren't isolated at all. They actually emerge together from incredibly simple progressive numerical systems.
What's fascinating here is that understanding Chen's paper completely shifts our worldview.
It really does. It's like finding out that all those different tools in your toolbox are actually just, I don't know, branches growing off the exact same tree.
Beautifully put. Instead of seeing mathematics as this messy, disjointed collection of random numbers you just have to memorize, you start to see it as a single growing organism, a unified structure where one thing naturally flows into the next.
Okay, let's unpack this, because Chen doesn't just drop this massive theory on us out of nowhere. I mean, he builds the case from the ground up.
Step by step.
Yeah. We're going to explore this journey with you, stepping through a series of mathematical roadblocks that Chen solves one by one.
We'll start with the basic problem of counting and geometry.
And by the end, we are going to arrive at a literal master sequence that seems to, well, generate the blueprint for math itself.
So the first major roadblock we have to tackle is building a bridge between two wildly different realms. On one side, you have discrete mathematics.
Which is basically just counting.
Right. Think of this as your standard whole numbers. 1, 2, 3, 4. It's rigid. It's countable. There are clear steps.
Okay, and the other side?
On the other side, you have continuous geometry, which deals with curves, slopes, and lengths that simply refuse to fit perfectly into whole numbers.
Ah, like square roots.
Exactly. Things like square roots, which go on forever in their decimal forms. They are fluid.
So it's basically oil and water, discrete and continuous. But Chen forces them to mix, and he starts by using something called the Theodorus spiral.
It's a great geometric tool.
Yeah. So if you're listening and trying to picture this, imagine drawing a classic right-angled triangle.
Yeah.
Make the two shorter sides, the legs, both exactly 1 unit long.
Right. Just a basic 1-by-1 right triangle.
Now, dusting off the old Pythagorean theorem for memory, that means the long slanted side, the hypotenuse, is the square root of 2.
And that forms the core seed of the whole system.
Okay, so how do we build the spiral?
To build a spiral, you take that new hypotenuse, the square root of 2, and you use it as the base leg for a brand new right triangle.
Oh, I see.
Yeah, you add another vertical leg that is exactly 1 unit long, calculate the hypotenuse for that new triangle, and you get the square root of 3.
And you just keep doing it. Do it again, add another leg of 1, and the next hypotenuse is the square root of 4, which is just 2.
Exactly. You just keep stacking these triangles, spiraling outward. It creates a literal physical fan shape.
And mathematically, it generates this pristine sequence of geometric growth, root 1, root 2, root 3, root 4, just going on to infinity.
But, sitting by itself is just a shape.
Right.
The magic happens when Chen introduces a secondary mechanism, a painfully simple, almost childish rule. He calls it an add-one recurrence.
Okay, so what does that actually mean?
He takes that continuous geometric sequence of square roots and forces a rigid, discrete action onto it. He simply adds the whole number 1 to each step.
Wait, literally just the square root of n plus 1.
That's it. The formula is just the square root of n plus 1.
I was trying to visualize how this actually generates anything meaningful, And here's what came to mind.
Let's hear it.
Think of that square root sequence like a smooth, continuously curving skateboard ramp. That's continuous geometry.
Okay, I can picture that.
Now, think of the +1 counting sequence as building rigid wooden stairs. When Chen forces those rigid stairs onto the curved ramp, the two shapes don't fit perfectly,
Yeah.
right?
There's a mismatch.
There's friction. And it's within that friction that these famous constants suddenly, spark into existence.
It's a great analogy, and the outputs are genuinely shocking when you actually run the numbers.
Tell me about it.
Let's say you take the square root of 3 from the spiral and add 1. The result is approximately 2.732.
Which is, wait, that's E?
Very close, yes.
Yeah.
That is a very close approximation of E, Euler's number.
That's crazy.
And if you move further up the spiral to the square root of 10 and add 1, you get roughly 4.162.
And let me guess.
That happens to be an approximation of pi plus 1.
It's just blowing my mind. Simply taking the square root of 2, adding 1, gives you the silver ratio. Taking the square root of 7, adding 1, gets you incredibly close to the golden ratio +2.
It really is wild.
We are taking the most mundane counting mechanism possible, throwing it against curving square roots, and the foundational constants of reality just start dropping out of the sky.
It proves a massive conceptual point. You can embed the logic of discrete counting directly into a continuous geometric framework, and the result isn't chaos.
It's a hierarchy of constants.
Exactly. However, this initial approach has a fatal flaw.
Oh!
It's essentially a goldfish. It has absolutely no memory.
Oh, I see what you mean. Every step is an isolated event.
Well,
Taking the square root of 10 plus 1 cares absolutely zero about what happened at the square root of 9.
right. It's a blank slate every single time.
And if we want to build the complex architecture of the universe, math needs a memory. Which brings us to the next problem Chen tackles. How do we fix the goldfish problem?
To give the system memory, Chen abandons the isolated square roots and moves us to a sequence built entirely out of its own past.
Okay.
He calls it the Fibonacci Pythagorean sequence, or the FP sequence for short.
Now, most of us know the classic Fibonacci sequence, right? 1, 1, 2, 3, 5, 8. You just take the last two numbers in the line, add them together, and you get the next one.
Exactly. It's simple addition. It remembers its past, but it's entirely flat. It's a straight line of arithmetic.
So how does the FP sequence change that?
Chen takes that concept of looking backward, but he swaps out the simple addition for geometric combination. He brings back the Pythagorean theorem.
Oh, wow.
Yeah. Instead of saying the next term is just number A plus number B, the rule becomes the next term is the square root of A squared plus B squared.
If you're listening to this and trying to mentally calculate squares and square roots in your head, don't worry about the actual numbers themselves.
Yeah, please don't give yourself a headache.
The vital takeaway here is the concept of what's happening. The sequence is constantly building new right triangles out of the old right triangles.
Yes, the old hypotenuse becomes the new leg.
So it is accumulating geometric history.
Exactly. And the sequence it generates looks like a geometric echo of Fibonacci. You get 1, the square root of 2, the square root of 3, the square root of 5, the square root of 8.
So it has memory now.
It does. But to extract the constants, Chen layers an arithmetic rule right on top of this geometric scaffolding. He calls it an add-to recurrence.
Which means?
He takes adjacent terms in this new geometric sequence and simply adds them together.
So he takes the third term, which is the square root of 2. He adds it to the fourth term, which is the square root of 3. And the result is 3.146.
Which is an astonishingly close approximation of pi.
Okay, I have to push back on this, though.
Go for it.
Because when I first read this part of the source, I had a full existential math crisis.
I don't blame you.
I have always thought of pi as a purely spatial concept. It's the ratio of a circle's circumference to its diameter, right? But Chen makes it sound like pi isn't about circles at all.
It's definitely a paradigm shift.
Are we actually saying pi is just a natural byproduct of geometric memory?
That is the profound realization Chen is pushing us toward. When a system accumulates information over time, which is essentially the definition of recursion, very specific inevitable structures emerge from that history.
Okay.
In a purely additive flat system, that accumulation produces the golden ratio.
Oh.
But in a geometric system that remembers its past, that accumulation produces pi.
That is insane.
It tells us that these higher-order constants aren't just arbitrary shapes floating in a void. They require a system with a past. They are the physical manifestation of accumulated mathematical structure.
So pi isn't just a circle. Pi is the shape of memory. That completely rewrites how I view the natural world.
It's a huge perspective shift.
But the journey doesn't stop there. So far, we solved the discrete continuous gap with the skateboard ramp and stairs. We solved the goldfish problem by building triangles out of old triangles.
Right.
But Chen starts asking a new question. What happens if we take two completely different systems with memory and force them to collide?
He calls this cross-interaction. He takes two completely separate recursive sequences and pairs them up.
Okay.
On one side, he brings in the classic Fibonacci sequence, representing our discrete arithmetic growth. And on the other side, he brings in the FP sequence we just discussed, representing our continuous geometric growth.
It's Frankenstein mathematics.
Pretty much.
It's like we're crossbreeding two entirely different math species to see what the offspring looks like. You have the discrete integer parent and the irrational continuous parent.
Yes, and Chen stitches them together by taking the nth term of the geometric sequence and adding it to the n-1 term of the classic Fibonacci sequence.
And the offspring of this pairing inherit incredibly complex traits from both parents.
Absolutely. When you run this cross-interaction, the constants don't just appear as isolated numbers anymore.
What do they do?
Well, because both parents brought their own deep recursive histories into the mix, the outputs start forming distinct mathematical families. Specifically, they cluster into groups of three.
This was wild to read. The numbers start spitting out approximations for the silver ratio cubed, e cubed, and pi cubed.
Yeah, powers of three.
For instance, if you march down to the 8th step of this Frankenstein pairing, you are taking the classic Fibonacci number 21 and adding it to the geometric term of the square root of 89.
And the result?
It comes out to roughly 30.43, which is an incredibly tight approximation of pi cubed.
If we connect this to the bigger picture, this specific experiment proves a major hypothesis of the entire paper.
Which is?
It demonstrates that if you want the truly rich, complex structural patterns of the universe to emerge, three foundational criteria absolutely must be present at the exact same time.
Okay, what are they?
You need discrete, step-by-step elements. You need continuous, fluid quantities. And you need recursion, a memory of the past. If you remove even one of those pillars, the complexity collapses.
It's a super elegant theory. But, I kept reading and realized this crossbreeding approach hits a pretty solid wall.
It does, unfortunately.
It successfully breeds approximations for pi, e, and phi, which is great. But it feels a bit brute force. It relies on very specific ad hoc pairings that Chen basically orchestrates.
It's not entirely organic.
Exactly. It's like a cool party trick that only works with a specific deck of cards. We haven't found the fundamental universal scaling element yet.
We haven't. And to solve that final limitation, Chen basically burns the house down.
Oh, boy.
He throws out the discrete integers, he throws out the square roots, the ad hoc pairings, the Frankenstein monsters. He strips the entire operation down to a single foundational building block.
And what does he replace it with?
He replaces everything with phi, the golden ratio.
The master key. Chen introduces the Fibonacci Pythagorean Kepler sequence, or the FBK sequence.
Yes, the FPK sequence.
And the formula for the sequence is, laughably simple compared to the crossbreeding we were just doing. It is defined purely by taking phi and raising it to half integer powers.
So the formula is just a sub n equals phi to the power of n divided by 2.
That's it.
What happens when you map this sequence out is where the elegance truly shines. Let's just look at the positive integer steps first.
Okay.
As your n variable goes 1, 2, 3, 4, the sequence generates steady exponential growth. If you calculate the actual decimal values for the first 20 terms and round them to the nearest whole number, the sequence does something remarkable.
What does it do?
It splits.
Here's where it gets really interesting. It splits into two perfectly interleaved sequences of whole numbers.
Yes.
The even steps give you 4, 7, 11, 18, 29. The odd steps give you 3, 5, 9, 14, 23.
And if you look closely at both of those lines, they are perfectly functioning Fibonacci-style sequences. 4 plus 7 is 11. 11 plus 7 is 18.
So the positive side of this single phi equation perfectly recreates the discrete counting memory we spent so much time trying to manually build earlier.
Exactly. It generates its own discrete structure naturally, but the positive steps are just the warm-up.
Oh, right.
When n drops into the negative numbers, the universe tears wide open.
I love that phrasing.
When you use negative exponents, you are no longer growing. You are creating reciprocal decay. You are dividing by larger and larger powers of phi, meaning the fractions are getting infinitely smaller.
Which is such a counterintuitive place to look for massive universal constants. We are diving into the microscopic fractions of math.
We are, but those incredibly small fractional steps act as a highly sensitive fine-tuning dial. As that sequence decays, it essentially scans the mathematical spectrum, locking on to the hidden frequencies of our universe.
And it starts spitting out emergent approximations for over 40 different vital mathematical constants.
And we're talking about an accuracy rate of over 98% for almost all of them.
The list in the source material just kept going. My jaw was on the floor. I mean, phi to the power of 2.5 approximates the bronze ratio.
Incredible.
If you scale the dial a bit, say multiplying by 100 and taking phi to the negative 11.5, you lock onto Euler's constant. And 1,000 times phi to the negative 12 perfectly approximates pi.
It generates the Conway constant, the Kepler-Beauchamp constant, and my personal favorite, the magic angle.
Okay, wait, stop. We can't just gloss over a name like the magic angle.
I knew you'd stop me there.
Let's bring that down to earth for a second, because this isn't just abstract number theory. The magic angle is a very real physical thing, right?
It is a profoundly physical phenomenon.
Okay.
If you take two unbelievably thin sheets of graphene, which is just carbon arranged in a hexagonal lattice,
Okay.
and you stack them on top of each other, they normally behave just like standard graphite, like pencil lead.
Makes sense.
But if you twist the top layer by a very specific angle, roughly 1.1 degrees, the material undergoes a miraculous transformation. It suddenly becomes a superconductor, meaning electricity flows through it with zero resistance.
And that 1.1 degree twist is the magic angle.
Exactly.
And what Chen's paper is showing is that this hyperspecific reality-bending angle that physicists only discovered recently in twisted graphene is just naturally sitting there waiting to be found as a negative power of the golden ratio.
It's like Chen found the source code for reality.
It really is. But the burning question is why? Out of all the numbers in existence, why is phi the ultimate master key that unlocks the geometry of circles, the memory of sequences, and the superconductivity of carbon?
It comes down to one uniquely elegant algebraic identity. Phi is the only positive number in the universe that satisfies this simple equation. 1 plus phi equals phi squared.
That is doing a massive amount of heavy lifting. Let's really break that equation down because it's essentially the crux of the whole deep dive.
On the left side of the equation, you have 1 plus phi. That is addition. That represents the discrete, linear, step-by-step logic of counting.
Got it.
On the right side, you have phi squared. That is exponentiation, which represents the continuous nonlinear logic of geometry.
Ah, I see.
Phi is the exact mathematical point where addition becomes multiplication. It is the bridge between the rigid and the fluid.
To ground that in reality, think about how nature actually grows. Look at a tree. A tree grows by adding a single branch. That's the left side of the equation, addition.
Right.
But as time goes on, that single branch splits and multiplies into smaller twigs, which multiply into leaves. That's the right side, multiplication.
That's a perfect way to visualize it.
Phi is the exact ratio where adding a new part perfectly transitions into multiplying the whole structure.
And by using phi as the foundational base, Chen's final system naturally incorporates recursion, geometric irrationality, and discrete step-by-step structure all at the exact same time.
It has all three pillars built into its DNA.
Exactly. You don't need to force the rigid stairs onto the curved ramp anymore. You don't need to genetically crossbreed sequences.
The phi-based geometric progression naturally scales across the numerical universe, hitting the resonant frequencies of all these seemingly unrelated constants.
Which is just, it's breathtaking.
So bringing this entire journey together for you, the listener, we started with a fundamental problem, right? Math felt like a box of disconnected tools.
A very messy box.
We tried to fix it by forcing rigid counting onto curving square roots and caught our first glimpse of constants emerging from the friction.
We then recognized that math needed a memory, discovering that constants like pi's aren't just spatial shapes, but the physical artifacts of accumulated historical growth.
Then we played mad scientists crossbreeding discrete and continuous sequences to prove that true complexity requires memory, counting, and geometry all working together.
And finally, we threw it all away to discover that phi, the point where adding becomes multiplying, acts as an infinite universal dial that generates nearly every major constant we know just by shifting its power. This is the ultimate payoff for anyone who loves learning. The pursuit of knowledge isn't about rote memorization, it's about finding the hidden architecture.
Yes.
Chen's work demonstrates that the mathematical universe isn't a fragmented mess. It is deeply, fundamentally cohesive.
So what does this all mean? It means the trauma of high school flashcards was built on a lie.
I wouldn't go that far, but yes.
These mathematical constants aren't arbitrary, isolated phenomena. They are just localized outputs of a single, highly structured numerical letter. When you look at pi or e or the magic angle of graphene, you aren't looking at different species of math.
You are looking at different branches growing out of the exact same tree.
Exactly.
This raises an important question, and it's the thought I want to leave you with to mull over.
Yeah.
Physicists and engineers use these incredibly diverse mathematical constants to literally describe the bounds of our reality. They use them to map the curvature of the universe, to calculate the orbits of planets, the decay of atoms, the flow of electricity.
They are the cheat codes that make the universe run.
But if all of these vastly different constants, the codes for gravity, circles, and quantum mechanics, are all just emergent approximations generated from a single 5-based sequence.
Yeah.
Does that mean the physical laws of our universe aren't actually a collection of different rules? Are we just looking at different zoom levels of one single infinite mathematical fractal?
Wow.
It suggests that the deepest complexities of our physical reality might just be the echoes of one beautifully simple recursive geometry.